Hi, the Fluid Power Training Institute have been building hydraulic, pneumatic and electrical trainers now for some 30 years. And today I'd like to talk to you about the model MF200 CAV cavitation training system. Pump cavitation is arguably one of the most difficult topics to teach students and to help them understand what pump cavitation actually is. And there's some confusion about cavitation because understood as starvation, and in others it's aeration of the oil. So which one is it? The transparent reservoir and transparent lines on the cavitation trainer help us understand cavitation because we can actually see it occur. So let me introduce you to the trainer itself. We have a reservoir which is mounted above the hydraulic pump. We've got a baffle. We've separated our intake and return lines, which is prudent design. We have a breather on the reservoir. This is a vented reservoir. And as we go down, we can see the large diameter tube that we have here. That is the pump intake. We've increased its size to obviously look at cavitation occur. The smaller diameter tube is the discharge line from the hydraulic pump. And let me just add, there is no pressure in these transmission lines. The pressure is in stainless steel tubing behind the panel. On the left-hand side, we have an analog flow meter, 0 to 2 GPM. And then we have a 4-inch vacuum gauge, 0 to 30 inches of mercury. Then we also have an ambient and oil temperature digital gauge. On the right-hand side, we have a 4-inch pressure gauge, 0 to 1000 psi. Down below is where we find all the controls. Here we have a valve that will allow us to let air enter the pump, which would simulate a cracked connector, loose clamp, etc. The next valve is going to allow us to restrict the flow going into the hydraulic pump, which is going to simulate a plugged screen, for example, in the tank, or a breather on the reservoir, which might be plugged. We have a 1.8 gallon per minute gear pump, and we have another valve which restricts flow so we can increase the pressure, because what we want to study, in addition to understanding what cavitation is how it affects the operation of a hydraulic system. We also, as with all of our products, everything we design and build is safety-based. So students are automatically going to learn all aspects of lockout and tagout. On our other products, we go further and we talk about detecting and diffusing stored energy. So I'm going to unlock the electrical switch on the trainer here so we can get ready to start it up. Now, if you look below the trainer, you'll see another reservoir. What we have done here is, which is very, very unique, is we've made it possible to actually, in real time, lower the oil level. That'll enable us to study what happens if we drop oil in on top of oil, meaning we neglect an oil level, a designer designs a hydraulic system and is not fully understanding of how vital it is to let any return flow discharge below the oil level. So that is a nice feature. The other nice thing about it is there's no manual work in getting the oil from the lower tank back into the upper tank. It automatically pumps the oil back, which we will see. So let's start it up. And what we will do is, this trainer comes with a really interesting curriculum, PowerPoint slides. It's a complete training system. There are 4 parts to the activity the student would undertake. The first one is what I like to refer to as get to know the patient. In other words, let's get to see what the normal operating parameters of this hydraulic system are. That's going to be lesson number 1. And that's important because in hydraulics, or like anything we maintain, is we have to know what normal is in order to detect an abnormal variation in the performance of a hydraulic component or a hydraulic system. Lesson 2 is understanding what cavitation is. Cavitation is the formation and collapse of gaseous cavities within a liquid. So looking at the oil in the reservoir, it's obviously not easy to detect. In fact, it's impossible to detect it. We have hydraulic oil has 10% dissolved air by volume. So up to and during cavitation, the dissolved air comes out of the oil, and of course that's where the cavitation comes from, as we will see. So lesson number 2 is all about cavitation. Lesson number 3 is about pseudo cavitation. When a condition is occurring, which sometimes people refer to as cavitation, because we don't know how to differentiate between the two, when a cavitation occurring that has nothing to do with either the dissolved air in the oil or a liquid's vapor pressure, then it's not actually cavitation. It's referred to as pseudo, the word pseudo meaning false cavitation. This is what happens when we allow air to enter the intake side of the pump. And this is very, very problematic. It's actually more detrimental to a hydraulic system than is cavitation, as we will see. So anytime we see foaming in the oil, this is usually a signature of pseudo-cavitation, but not cavitation. Finally, what we will do in lesson number 4 is we will allow the oil level to drop in real time until the discharge line is above the oil level. This is an interesting thing to see, because since we have backlit the oil to make this to make it obvious to see it, we will see a tremendous amount of turbulence occurring where the oil is returning or dropping in above the oil, which again, like pseudo-cavitation, aerates the oil and of course causes the oil to foam. Also a systemic catastrophic condition. One other thing we'll see as the oil level begins to drop is it'll get to a level where on the intake side we will see an actual vortex occur. Another phenomenon that's very interesting, because we can actually have air in a hydraulic system even though we're not exposing the intake of the pump directly to the atmosphere. So let's start it up, and then let's look at first the normal operating parameters of the system. All right, so we start out with the flow rate. We have 1.8 gallons per minute. The next thing we'll notice is that we have a normal inlet restriction here of 5 inches of mercury. Now this is critical. This is very important. The reason why that's important is because the manufacturer, by rule of thumb, the maximum inlet restriction in a gear pump is 8 inches of mercury at normal operating temperature. That's about 135 degrees Fahrenheit. So that is what the manufacturer of the gear pump recommends. So let's just understand that. The manufacturer of the gear pump tells the design engineer, gives the design engineer a parameter which the design engineer has to stay within. And that number is approximately 8 inches of mercury. Once that has been established, the responsibility of the design engineer is when he or she commissions the machine, the hydraulic system, it is vital to be able to go out to the pump and establish that I am within the manufacturer of the pump's specifications on inlet restriction. That's vital. So in other words, if the manufacturer in this case says the inlet restriction is 8 inches of mercury, and as we can see we're at 5 inches of mercury, that means we are well within that specification. It'll also get better because the oil temperature right now is 75 degrees Fahrenheit, so it's only going to get better as the oil temperature increases and the oil viscosity decreases. This is a vital number because this then also becomes the information that goes to the maintenance personnel. That is, the number that the maintenance people work with is this number here, 5 inches of mercury. This is what we call a point of reference for inlet restriction on a pump. and that's vital. Once we have the point of reference, then what is vital is that every 30 days, based on an 8-hour shift, we monitor that to make sure that we don't either go above or below the point of reference. Anytime the inlet restriction rises above, in this case, 5 inches of mercury, it's a red flag that there is something wrong at the inlet side of the pump. On the other hand, if we go down below 5 inches of mercury, even though theoretically lower is better, if we go lower than our point of reference, we have to be concerned. That is, are we getting air in? Because it's easier for a pump to take in air than it is to take in oil. So the thing that I'm going to have to look for is, am I getting air in? Is my oil foaming? This is a systemic catastrophic situation. All right, so we'll come back to that again in just a moment. So right now, we've established our point of reference, and we've got to know our patient with respect to our flow rate, our inlet restriction. We have now set the resistance to flow in our pump at 700 psi, because we want some pressure in order to listen to the noise that cavitation will generate, which will yield. A few things that are important to note, since it's obvious that design engineers seldom get the opportunity, neither do maintenance people, to see exactly what the oil in a reservoir looks like, or in the oil transmission lines when the system is actually running. Right now, as we look at the inlet to the pump, the oil that is coming out of the reservoir going into the pump, it is impossible to even see that right now, every 60 seconds there is 1.8 GPM flowing through the transmission line. Likewise, on the pressure line, it's virtually impossible to see that the oil is actually flowing. This is commonly referred to as laminar flow, and this is an ideal operating characteristic. There is also no evidence of movement of any type of turbulence in the reservoir. This is an ideal operating scenario. Now, what I'm going to do is I'm going to now increase inlet restriction by gradually using this valve, gradually restricting the flow, thereby increasing inlet restriction. What you will notice is that when I reach a certain point, and it's a very small window, when I reach a certain point, you will suddenly see the dissolved air coming out of the oil. This is very similar to opening a pop bottle. In other words, if I've got a bottle of translucent pop, which is under pressure, and I take the top off, all of a sudden we will see the dissolved or the gases coming out of the liquid. Hydraulic oil will do exactly the same thing if I subject it to a vacuum, which I'm about to do. I'm going to take the inlet restriction above the threshold temperature that is given as a maximum by the manufacturer. Let's see what happens. As I slowly increase resistance to flow into the pump with my valve, I can see my inlet restriction going up on the vacuum gauge, and then I'll reach a point where all of a sudden the dissolved air is going to come out of the oil. It is clearly obvious now that I am forming these gaseous cavities, which are alive and well in the intake, but as the gaseous cavity goes through the pump and the implosion occurs, the gaseous cavity disappears. It goes back into suspension. Notice a few things. Number one, I've dropped my flow from 1.8 GPM down to 1.5. I'm losing power. Two, I have dropped my pressure from 700 psi down to 450 psi. So I'm losing both flow and pressure. This is symptomatic of cavitation, noise, flow reduction, and also a reduction in pressure. Notice a few things. First and foremost, there is no indication that there's cavitation in the pressure line. There's no indication at all. Number one. Number two, there is absolutely no evidence cavitation is occurring in the reservoir. In other words, as people sometimes believe, if they see foam in the reservoir, it's automatically cavitation. Well, actually it's not, because as you can see, the pump is cavitating violently right now, and there's no evidence of it anywhere other than at the intake of the pump. Now, this is systemically harmful to a hydraulic system, in that, obviously, cavitation, if you've got an implosion occurring in a pump, it's ripping, so to speak, ripping little pieces of the pump out and feeding them downline. Well, as we know, any piece of contamination we feed downline is an abrasive seed, and its growth is exponential. So it is systemic from that point of view. Not as harmful, however, as pseudo-cavitation. In other words, oil has four purposes. Number one, we transmit power with the oil. Two, we lubricate with oil. Three, we seal with the oil. And four, we dissipate heat with oil. Well, throughout my system, I haven't affected the purpose of the oil outside of the damage that is localized into the pump. This is cavitation. Now, let me take this condition away, and let's move to step 3. Now, obviously, when this is done as a student activity, it's a little slower because there's a lot of discussion, there's information that the students have to fill out about what they're observing, and so on. The next thing I'm going to do now as we move on to number 3 is, bear in mind that our point of reference was 5 inches of mercury. When we increased the resistance to flow into the pump, we increased it, we created a condition which we call cavitation. This occurs when the inlet restriction is higher than normal. Now I'm going to go to the flip side of the coin. I'm going to allow air to go into the intake of the pump, and you will see that inlet restriction will then become lower than normal. So contrary to popular belief, lower is not better if I don't have a point of reference. So now, look at the remarkable difference between cavitation and pseudo-cavitation. I'm going to open this valve here, which is going to let the smallest amount of air, almost like a hairline crack in a fitting, go into the intake of the pump. So here we go. I'm going to immediately see a decrease in inlet restriction as the air starts to go into the intake of the pump, and I will start to see air mixing with the oil at the intake here. Here it comes. Interestingly, it'll go through now, through the pump, out the other side, and it'll start pumping it through the system, and eventually it'll start pumping it into the reservoir. And it'll almost look as though the oil is boiling. So in a moment, this will become highly turbulent. Again, inlet restriction, my point of reference was 5 inches of mercury. I am now down at 1.5 inches of mercury, and I've got a continuous infeed of air to the intake, which has converted my hydraulic pump, for all intents and purposes, into a semi-oil pump, semi-air compressor. As you can see, the cloud of air that is forming above the oil level and spreading across the entire reservoir. This is a highly undesirable situation because it's going to create widespread damage. Again, back to the purpose of the oil. 1, transmit power. I am losing, my flow is fluctuating between about 1.6 GPM and about 1 GPM. very violent fluctuations. My pressure is fluctuating between 600 and 100 psi. Violent pressure fluctuations. Next, so I've lost power. I'm going to lose power. Next, the oil we use to lubricate. There is no way we can lubricate with what we see here. Let me just turn this off for a second just so that we can see what this looks like. All right. So there's no way we can transmit power with what we see here, number one. Number two, we cannot lubricate. So throughout our system, we've got this oil that is foamy, which means I've lost lubrication, my lubrication between my wearing parts, my moving parts. The next thing that is going to occur is I can't seal with foam, oil which is foamy. And last but not least, there is no way I can carry heat away with oil that is air contaminated, as you can see here. Sometimes people will look at the sight glass in a hydraulic tank and they'll see this light color, and they will confuse this air contamination of the oil with actually water contamination of the oil, because water will also change the complexion of the hydraulic oil. So as you can clearly see, the oil is now, if I leave this, if I continue to run the simulator, this is growing the oil level. In fact, it's been known to actually foam out through the breather. That's how bad it can get. This condition does not destroy the oil. It will settle out after a while. In this particular trainer, it'll settle out after about 10 to 15 minutes. It'll go back to normal. So again, we are now on lesson number 3. 3 is a study of pseudo cavitation, and pseudo cavitation occurs when air is going into the intake of the pump. This can occur typically low oil level, loose connectors, etc., at the intake of the pump. A widespread systemic disaster. This has to be nipped in the bud. Never ever allow a hydraulic system to continue to operate when the oil looks like what you see in this particular reservoir. Now, let's go to the last lesson here. What I'm going to do again is I'm going to start it up. And now it would be actually prudent for me to let it settle out, let this air settle out. In fact, I'm going to do that. Now we've allowed the oil to normalize. So now I'd like to demonstrate what happens when oil is dropping in, if you will, on top of oil that's in an existing hydraulic reservoir. Once again, this is going to create a condition called pseudo-cavitation. Why? Because the turbulence is going to aerate the oil, and of course it's going to cause the pseudo-cavitation once again. So let's start it up. Now what I'm going to do is I'm going to open a valve. There's a valve at the back of the hydraulic trainer that will drain the oil out of the upper reservoir down into the lower reservoir. It's relatively slow, so it takes a minute for the oil level to drop to where this white return line is above the oil. So bear in mind, I'm going to be dropping 1.8 GPM, gallons per minute, in on top of the oil in the reservoir. You will start to see violent turbulence in about this area where the oil is dropping in on top of the oil, and once again, you'll see the oil begin to aerate. And again, this is pseudo-cavitation. So here's where it happens now. So I'm now out of the oil level. My return oil is dropping in above the oil, and I have turbulence in just below the area where the oil is dropping in. And of course, as you can see, as I take the oil level away from the return line, it gets exponentially worse. So let's now, as we can see here, so this is again aerating the oil. This is again pseudo-cavitation. Look to the other side of the baffle and you will see very clearly a vortex developing in the oil. In other words, this is now staging down. It's designed to, first of all, let us study what happens when we drop oil in top of oil, and then we go down a little further, and this is all done automatically. We can study vortex at the intake of the pump. So again, we've got this condition called cavitation.